I want you to envision the cosmos in its earliest conceivable stage, a time so far removed from us that the very fabric of time operated differently. In the instant following the universe's explosive birth, a moment that created space itself, the cosmos was an intensely hot, dense, and chaotic brew of fundamental particles and energy. During this era, familiar atoms were unable to form, and light remained ensnared, perpetually scattered by charged plasma particles, much like sunlight trying to cut through a dense fog. As the universe expanded, it also cooled down. This gradual, relentless cooling process unfolded over hundreds of thousands of years. Approximately 380,000 years after the beginning, the cosmic temperature fell to about 3,000 degrees Celsius. This was just cool enough for free-roaming electrons to finally be captured by protons and helium nuclei, creating the first stable and electrically neutral atoms, in an event astronomers refer to as the epoch of recombination. Once electrons were bound in orbit around atomic nuclei, they ceased to scatter photons, the particles of light. In that instant, the previously opaque universe became transparent. The very radiation released during this event is what we now detect as the cosmic microwave background, the relic radiation. It's a faint, ancient echo of the Big Bang that reaches us from every direction in the sky. But this did not usher in an age of light. Although the cosmos was now clear, there were no new objects to generate light. The cosmic microwave background was just the fading glow of a former fiery epoch, and it continued to dim and cool as space expanded. With no stars, galaxies, or quasars to illuminate the void, the universe entered a period that scientists have fittingly termed the Cosmic Dark Ages. Try to imagine a boundless, ever-expanding space filled with a thin, neutral gas composed of roughly 75% hydrogen and 25% helium, plus minuscule traces of lithium. Nothing more complex than this existed. All other chemical elements had yet to be forged inside the nuclear furnaces of the first stars. This primordial gas was dark, cold, and sinking into a profound, pervasive blackness that would endure for hundreds of millions of years, marking a period of stillness and anticipation. The universe at this time was astonishingly uniform, but crucially, it was not perfect. Had it been entirely smooth, nothing would have ever taken shape. The gas would have just kept expanding and cooling into oblivion. In the first fractions of a second after the Big Bang, during a phase of incredibly rapid expansion known as inflation, minuscule quantum fluctuations were stretched to cosmic proportions. These created almost imperceptible variations in density, ripples in the distribution of matter that were incredibly small, deviating by only about 100,000%. Yet these tiny imperfections were the seeds from which all future cosmic structures, including stars and galaxies, would eventually grow. At this point, a mysterious and pivotal force joins the narrative: dark matter. You cannot see it, as it neither emits nor absorbs light, but its existence is confirmed by the gravitational pull it exerts on matter we can observe. Dark matter is about 5 times more prevalent than the ordinary baryonic matter that constitutes you, me, the planets, and the stars. Because it doesn't interact with light, it was free from the radiation pressure that kept ordinary matter in a constant state of flux. This allowed dark matter to begin clumping together early on, drawn by its own gravity into the regions with slightly higher density. These invisible concentrations of dark matter formed what scientists call halos, which essentially served as gravitational wells. When the epoch of recombination occurred and ordinary gas became neutral, it was finally released from the relentless pressure of light and could respond to gravity's pull. This neutral hydrogen and helium began to slowly but surely drift into the dark matter halos, gathering like water flowing into a basin. These halos provided an unseen gravitational framework that dictated where visible matter would assemble, dramatically accelerating the formation of the first cosmic structures. So, the scene of the cosmic dark ages can be summarized as a vast, cold, and expanding universe filled with neutral hydrogen, helium, and invisible dark matter. The ancient light of the cosmic microwave background traveled freely through this emptiness, but no new sources of light existed. Beneath this veil of darkness, however, the invisible hand of gravity was tirelessly at work, gathering the primordial gas into the gravitational traps set by dark matter, preparing the stage for the birth of the first stars. This entire period was a silent, grand drama orchestrated by gravity, a time of unseen processes laying the foundation for everything you see in the cosmos today. Every particle of hydrogen, helium, and dark matter was playing its part in a magnificent prelude to the era of light. The universe was patiently gathering its strength, waiting for the first dawn that would finally end the long cosmic night. Gravity, the universe's relentless and ever-present force, ultimately took on the role of the primary sculptor for the emerging cosmos. You might recall those minuscule, nearly undetectable fluctuations in density that were a relic from the universe's earliest moments. These slight imperfections on an otherwise uniform canvas became the focal points for gravity's influence, as the force has a remarkable tendency to amplify itself. Wherever there was a slightly greater concentration of matter, the gravitational pull was marginally stronger, which in turn attracted more surrounding material, particles of dark matter, along with hydrogen and helium atoms. As this material accumulated, the density of the region grew, strengthening its gravitational field and enabling it to pull in matter from even farther away with increasing efficiency. This set into motion a kind of cosmic snowball effect, where the larger an object becomes, the faster it can grow. In the context of the universe, however, this process unfolded over immense timescales, spanning tens and even hundreds of millions of years, and involved not snow, but vast clouds of invisible dark matter and diffuse gas. Because dark matter does not interact with light and is immune to its pressure, it could start to coalesce earlier and more effectively than ordinary matter. It was the first substance to answer the gravitational summons of those primordial density fluctuations. Dark matter gathered into enormous, unseen structures that astrophysicists refer to as dark matter halos. These are spherical or slightly flattened clouds of particles that, while invisible to us, possess tremendous mass, with the smallest ones, known as mini-halos, potentially containing tens of thousands to millions of times the mass of our Sun. Despite their enormous mass, these halos spanned thousands of light-years, and initially had a very low density, resembling invisible gravitational wells or valleys scattered throughout the cosmos. As soon as ordinary matter, composed of hydrogen and helium atoms, was liberated from the pressure of light during the era of recombination, it began to succumb to the pull of these gravitational wells forged by dark matter. Neutral gas atoms, drifting freely in space, initiated their long, slow descent into these unseen valleys, nourishing the cores of the dark matter halos, in a process akin to a cosmic rain. Unlike dark matter, Ordinary gas was subject to its own internal pressure, which resisted compression, making its concentration a slower and more intricate affair than the formation of the dark matter halos themselves. Gas gradually collected inside these halos, its density steadily increasing in the central regions. This process led to the formation of the first purely gaseous clouds, not yet stars, but already significant accumulations of matter, brought together by the persistent pull of gravity. These primordial gas clouds were the nurseries for future stars, each containing thousands or even tens of thousands of solar masses of gas, all concentrated within a far more massive halo of dark matter. Their most crucial feature, however, was their extremely simple chemical composition. They consisted almost exclusively of the hydrogen and helium produced during the Big Bang, with a complete absence of the heavy elements such as carbon, oxygen, nitrogen, or iron that astronomers collectively refer to as metals, as these elements simply had not been created yet. This pristine composition profoundly affected the destiny of these clouds, as the lack of metals deprived the gas of effective mechanisms for dissipating the heat generated during gravitational compression. Although small quantities of molecular hydrogen, or H2, could form and radiate some energy, it was incredibly inefficient compared to atoms and molecules containing carbon or oxygen, which function like thermostats in modern gas clouds. This inefficient cooling would be the decisive factor in shaping the characteristics of the very first stars to ignite within these primordial nurseries. For the time being, these clouds continued their slow contraction under their own gravity, heating up from the compression, while only reluctantly releasing that heat into the surrounding void. They represented the first islands of heightened density in the vast ocean of the expanding universe, the initial triumphs of gravity's titanic effort to gather the scattered legacy of the Big Bang. The process was unstoppable. Gravity pulled the gas inward, pressure pushed outward, and the gas struggled to cool enough to continue its collapse, setting the stage for the next cosmic leap. The universe was preparing for the moment when the density and temperature deep within these primordial clouds would cross a critical threshold, igniting the first fire in the cosmic darkness. These initial clumps were not yet stars, but they were their direct progenitors, the seeds of light, planted in the fertile ground of the Dark Ages by the invisible hand of gravity. In the depths of the unseen dark matter halos, enormous clouds of primordial gas had now gathered, poised to break the monotonous darkness of the cosmic dawn. However, simply amassing gas in one location is not enough to birth a star. For a thermonuclear fire to ignite in its core, the cloud must be compressed to extraordinary densities and temperatures. Here, the first stars encountered a significant hurdle: the problem of cooling. In contemporary gas clouds where stars like our Sun are born, the process of compression is far more straightforward. Thanks to the presence of heavy elements and dust, radiators like carbon atoms, oxygen atoms, and carbon monoxide molecules, along with tiny dust grains, efficiently carry away excess heat in the infrared spectrum as the gas compresses, allowing the collapse to proceed smoothly. When gas cools down, it loses the internal pressure that once resisted compression, allowing gravity to resume its work and contract the cloud even further. This effective cooling process enables the cloud to fragment with ease, splitting into numerous, small, dense clumps, each capable of collapsing to form an individual star. This is precisely why, within contemporary star-forming regions, stars typically emerge in clusters and possess masses that are comparable to, or even smaller than, our own Sun. However, The circumstances within the primordial clouds of the early universe were starkly different. In that era, there was no carbon, no oxygen, and no dust. Essentially, nothing that could efficiently radiate away heat. The only notable cooling mechanism available to the hydrogen-helium gas was the emission of energy from hydrogen molecules, a small quantity of which could form within the densest and coldest pockets of the cloud. Molecular hydrogen is capable of radiating energy when its molecules shift between different rotational or vibrational states, which releases a photon in the process. Yet, compared to molecules like carbon monoxide or even individual carbon atoms, molecular hydrogen is an exceptionally poor coolant. It can only reduce the gas temperature to a few hundred Kelvin, somewhere between 170 and 200 to 300 degrees Celsius, and it accomplishes this very slowly. As the ongoing compression caused the gas to heat up, the cooling efficiency provided by H2 molecules plummeted. So, what did this actually entail? Gravity relentlessly pulled the gas inward toward the cloud's center, causing it to compress and heat up. But the gas had almost no way to release this accumulating thermal energy. The internal pressure, driven by the rising temperature, surged and powerfully opposed any further compression, forcing gravity to overcome a much greater level of resistance than it faces in modern clouds. Crucially, this inefficient cooling prevented the cloud from easily breaking apart into smaller pieces. For a specific region within the cloud to overcome its internal pressure and initiate an independent collapse, a threshold defined by the gene's mass, it had to be exceptionally massive, far more so than the typical fragments seen in clouds today. Instead of shattering into hundreds or thousands of tiny stellar embryos, the primordial gas cloud was more inclined to collapse as a single entity, or to form just a handful of very large gravitational centers. Consequently, deep within the collapsing giant cloud, which held tens of thousands of solar masses worth of gas, one, or perhaps several, tremendously massive protostellar embryos started to take shape. Gas from the surrounding cloud continued to spiral onto this central object, fueling its rapid growth as it accumulated mass at a phenomenal rate. You can picture this as a colossal whirlpool of hydrogen and helium swirling around a gravitational focal point, where the density and temperature just keep climbing. Gravity had played its part, setting the stage for the birth of the very first stars, which were destined to finally end the prolonged cosmic night. This slow but inexorable compression continued for millions of years, causing the gas at the center to become ever denser. Atoms collided with increasing frequency and force, driving the pressure in the core of this future stellar giant to unimaginable heights, while the temperature skyrocketed into the millions of degrees. Then, the moment arrived that the universe had been anticipating for hundreds of millions of years. In the very heart of this supermassive protostellar core, the temperature crossed the critical threshold of approximately 10 million degrees Celsius. At such extreme temperatures and under immense pressure, the protons within hydrogen nuclei, which normally repel one another due to their like positive charges, acquired enough energy to breach this repulsive barrier, allowing powerful nuclear forces to take control and initiate thermonuclear reactions. The process of fusing hydrogen nuclei into helium nuclei had begun. Through a sequence of intermediate reactions called the proton-proton cycle, 4 protons would combine to create a single helium nucleus. The critical detail here is that the resulting helium nucleus had a slightly smaller mass than the combined mass of the 4 initial protons. This missing mass was converted directly into pure energy, as described by Einstein's renowned equation, E=mc². A thermonuclear furnace ignited in the protostar's core, unleashing a tremendous flood of energy in the form of high-energy photons, gamma rays, and neutrinos. This outward surge of energy generated a powerful radiation pressure that ultimately counteracted any further gravitational collapse. The contraction ceased, the object stabilized, and a star was born. But this was no ordinary star. It was the first star in the universe, a member of the class known as Population 3, and it was a true giant. Its immense mass, perhaps 100, 200, or by some estimates, as much as 1,000 times that of our Sun, was a direct result of the unique formation conditions, especially the inefficient cooling of the primordial gas. The birth of this first star represented a fundamental turning point. This initial thermonuclear fire, forged by gravity from primordial hydrogen and helium, pierced through the gloom of the cosmic dark ages. The photons generated in its scorching core embarked on their long journey to the surface, gradually shedding energy through countless collisions with stellar matter, before finally bursting out into the surrounding space. This was the first light not from some fleeting explosion, but from a new, steadily burning star, and it illuminated its cosmic neighborhood. The infant universe was no longer steeped in complete darkness. The first lights had been switched on. As the first stars blazed to life, they tore through the ancient darkness of the early cosmos. But what were these cosmic pioneers, these trailblazers of light, actually like? You should set aside the familiar image of our Sun, or even the brilliant blue giants visible in the Milky Way today. The stars astronomers referred to as Population 3 were a completely different kind of celestial object, born under unique and unrepeatable circumstances. Their portraits reveal them to be true titans, monstrous by the standards of modern stars, beings of both incredible power and incredible transience. Above all else, the single most defining characteristic that set them apart was their colossal mass. As you're likely aware, the ancient gas that gave birth to these first stars was virtually devoid of heavy elements, which made the cooling process during their gravitational collapse incredibly inefficient. Unlike today, these gas clouds couldn't easily break apart into numerous, smaller clumps. Instead, gravity pulled vast quantities of matter into a single location, resulting in the creation of stellar embryos with truly monstrous mass. While the precise figures are still a topic of intense research and computational modeling, the scientific consensus is that the first stars typically had masses tens, or more likely hundreds, of times greater than our Sun. I want you to imagine a star 100, 200, or maybe even 500 times more massive than the Sun. This wasn't merely a large star. It was a genuine cosmic behemoth. Such extraordinary mass naturally led to colossal dimensions. Although a star's radius would have fluctuated during its brief existence, it's certain that these bodies were many times larger than the Sun. They were so immense that if one were to replace our star, its outer atmosphere would have completely swallowed the orbits of the inner planets. These were swollen, brilliant spheres on an almost unimaginable scale. Yet, their temperature was even more staggering. The immense mass generated unbelievable gravitational pressure at the star's core. To counteract this force and prevent collapsing under its own weight, the star had to produce a phenomenal amount of energy through thermonuclear fusion. This furious energy, rushing to the surface, heated it to temperatures that dwarfed the sun's surface of roughly 5,000 degrees Celsius, reaching tens of thousands, or possibly over 100,000 degrees. At such extreme temperatures, the star wouldn't have glowed with the yellow-white light of our sun, or even the blue light typical of massive modern stars. Instead, it would have emitted a blindingly intense bluish-white or even violet light, with the vast majority of its radiation concentrated in the harsh ultraviolet spectrum. This was a searing, sterilizing radiance, powerful enough to obliterate molecules and ionize atoms across enormous distances. The combination of their gigantic size and incredibly high surface temperatures resulted in luminosities that were nothing short of astronomical. They shone millions, or perhaps even billions of times more brightly than our own sun. A single one of these stellar pioneers could outshine an entire developing galaxy made up of millions of later generation stars. They were the most brilliant individual objects in the early universe, true cosmic lighthouses, whose fleeting light illuminated vast expanses of space. Of course, the defining trait that shaped all their other properties was their singular chemical makeup. The first stars were chemically pristine, composed almost entirely of the hydrogen and helium forged in the Big Bang. They lacked any carbon, oxygen, nitrogen, or iron, elements you're accustomed to finding in the Sun and other stars in our galaxy, where they constitute a small fraction of about 1 to 2%. This primordial purity was both their defining feature and their undoing, as the absence of these metals is what forced them to grow to such gigantic masses and develop such extreme characteristics. However, this incredible power came with a steep cost. The colossal mass and the frenetic pace of thermonuclear reactions needed to support these giants resulted in an exceedingly brief lifespan. A fundamental principle in astrophysics dictates that the more massive a star is, the shorter its existence. While our sun will shine steadily for about 10 billion years, the lives of these population 3 monsters were measured in just a few million years, perhaps 3, maybe 10 million at most. They were born from spectacular collapses, shone with unparalleled brilliance, and then made a swift exit from the cosmic stage. This, then, is the portrait of the universe's firstborn stars. Gigantic, intensely hot, and dazzlingly bright titans made solely of pure hydrogen and helium. Their reign was brief, lasting only a few million years, but in that short time, they irrevocably altered the trajectory of cosmic history. These were stars of extremes, products of conditions that will never be replicated, and their short but turbulent lives prepared the universe for everything that would follow. Every great performance has its finale, and the brilliant yet transient dominion of the first stars was no exception. Their incredible mass and furious luminosity were not just the source of their splendor, but also the guarantee of their rapid demise. They burned out in a thermonuclear blaze after only a few million years, a mere blink of an eye compared to the billions of years granted to stars like our sun. Their death, however, was not a quiet fading, but a cataclysmic event that reshaped the very fabric of the cosmos and planted the seeds for everything we see today, including ourselves. Try to picture the core of one of these population 3 monsters at the end of its short life. Deep inside, the primary fuel source, hydrogen, was inevitably being depleted. As hydrogen fused into helium, the core contracted under its own gravity, growing ever denser and hotter. This compression eventually pushed the temperature and pressure to new critical thresholds, high enough to ignite the next stage of fusion, the burning of helium through a process known as the triple alpha reaction, where 3 helium nuclei combine to form a carbon nucleus. Once the helium in the core was exhausted, the cycle repeated itself. The core would contract and heat up again until it became hot enough to fuse carbon, which was then followed by the burning of neon, oxygen, and silicon. Each successive stage of fusion demanded even more extreme temperatures and pressures, and each one proceeded at an even more accelerated pace, pushing the star toward its ultimate fate. If you could have peered inside one of the first stars, you would have seen a structure like an onion. At its very core lay the heaviest elements it had created, all the way up to iron, which was enveloped by successive layers of burning lighter elements: silicon, oxygen, neon, carbon, helium, and an untouched outer shell of hydrogen. It was within these stellar furnaces that for the first time the universe saw the birth of significant amounts of elements heavier than helium, forging the building blocks for planets and life itself. Prior to this, the cosmos consisted almost entirely of hydrogen, helium, and trace amounts of lithium. Now, these pioneering stars were manufacturing carbon, the foundation of all organic life, oxygen, the air we breathe, and silicon, the primary component of Earth's crust. However, this process of elemental synthesis had a natural limit. Once the star's core filled with iron, it reached a point of no return, as fusing iron nuclei consumes energy rather than releasing it, robbing the core of its ability to counteract the relentless pull of gravity. For the most gigantic of these first stars, those with masses exceeding 140 times that of our Sun, an even more spectacular and destructive end was in store: a pair instability supernova. Inside their incredibly hot cores, where temperatures soared past 1 billion degrees, a strange phenomenon unfolded. The high-energy gamma photons generated by nuclear reactions became so powerful that they could spontaneously convert into pairs of particles, an electron and its antimatter counterpart, the positron. This transformation of energy into mass, a concept predicted by Einstein's theory of relativity, proved fatal for the star. The very photons that had been providing the radiation pressure to support the core were now being consumed to create these particle pairs, causing the pressure to plummet. With nothing left to effectively resist it, gravity took control, and the core began a catastrophic collapse. Yet, this collapse did not result in a neutron star or a black hole as is common with other supernovae. Instead, the rapid compression and the subsequent spike in temperature triggered a runaway thermonuclear detonation of the remaining oxygen and silicon in the core's outer layers. In a fraction of a second, an immense quantity of energy was unleashed, which didn't just blow away the star's exterior, but completely annihilated it. This explosion was monstrously powerful, perhaps 100 times more energetic than an ordinary supernova, and it left no compact remnant, no neutron star, no black hole in its wake. Every element forged within the star throughout its existence, along with those created in its final moments, was violently ejected into the surrounding cosmos. While stars with slightly less mass might have exploded in a more conventional way, leaving behind a black hole, and even larger ones might have collapsed directly without a major explosion, it was the pair instability supernovae that served as the ideal mechanism for enriching the early universe with heavy elements. Picture this. After millions of years of brilliance, a giant star vanishes in a blinding flash of unimaginable power. In its place, an expanding cloud of gas remains, but it's no longer the pristine primordial mixture of hydrogen and helium. This cloud is now enriched with a precious cargo, the first atoms of carbon, oxygen, nitrogen, silicon, sulfur, and iron ever to exist in the universe. The shock wave from the explosion carried these newborn elements across the void, seeding the cosmos for the first time. The death of each of these first stars was not an ending, but a new beginning. Their explosions distributed the building blocks needed for subsequent generations of stars, which could now form with traces of these metals. This enrichment fundamentally changed the physics of gas clouds, enabling them to cool more efficiently and fragment into smaller bodies, leading to the birth of lower-mass stars like our Sun, capable of living for billions of years, and eventually, rocky planets like Earth. Every atom in your body, excluding hydrogen and some helium, was once forged in the heart of a star and scattered through space by its explosive death. It was these short-lived but critically important population 3 stars that set this cosmic cycle in motion. Their grand finale was the prologue to the creation of the complex, chemically diverse universe we live in today. The era of these titans was as brilliant as it was fleeting. In just a few million years they vanished in grand explosions. But their sacrifice gave life to the cosmos as you know it. And yet, within their brief existence, these stars fundamentally reshaped everything. Their short lives and spectacular deaths permanently re-engineered the cosmos, creating the very foundation for all that you see around you today. Their legacy was twofold. They banished the cosmic darkness and, simultaneously, infused the universe with a new palette of elements and potential. Their powerful, hard ultraviolet radiation served as the principal force that brought an end to the cosmic dark ages. You may recall that following the era of recombination, the universe was filled with a fog of neutral hydrogen and helium. While this gas was transparent to the cosmic microwave background, the residual thermal radiation that pervades all of space, it blocked more energetic photons and, crucially, produced no light of its own. The first stars unleashed torrents of photons with sufficient energy to strip electrons from neutral hydrogen atoms, converting them back into ions in a process known as ionization. Around each of these pioneering stars, an immense bubble of hot, ionized gas began to swell, carving out a region where the darkness retreated and ultraviolet light could once again travel freely. As countless more stars ignited, these bubbles expanded and merged. It's also possible that the earliest quasars, the intensely bright, active centers of galaxies, powered by supermassive black holes which may have formed from the remains of the most massive first stars, also played a part in this transformation. Over the subsequent hundreds of millions of years, these pockets of ionized gas grew until they encompassed nearly the entire expanse of the universe. This period, during which the majority of the universe's hydrogen became ionized once more, is known as the epoch of reionization, and it marked the conclusive end of the cosmic dark ages. The cosmos became transparent again, but this time it was not merely clear. It was now filled with the brilliant light of nascent stars and galaxies, whose rays could travel unimpeded for billions of light years through the ionized intergalactic medium. These first stars, having initiated this grand process, transformed a dark, neutral cosmos into the bright, ionized plasma that still characterizes intergalactic space to this day. Their second, and perhaps even more profound contribution, was to perform the first act of cosmic alchemy. It was within their scorching cores and during their cataclysmic supernova explosions, especially the type known as pair instability supernovae, that the first heavy elements were forged: carbon, oxygen, nitrogen, silicon, iron, and a host of others. Prior to their emergence, the universe had been chemically simple and monotonous. But as these newly minted elements were blasted into space by stellar explosions, they began to enrich the pristine hydrogen-helium gas, an act of pollution that had revolutionary outcomes. Even minuscule traces of these elements, which astronomers call metals, profoundly changed the characteristics of interstellar gas, primarily by enabling it to cool with much greater efficiency. Ions and atoms of carbon and oxygen, along with molecules like carbon monoxide and dust particles that later formed from these elements, acted as excellent radiators, allowing collapsing clouds of gas to shed heat far more effectively. This critical change permitted the formation of population 2 stars, the category our own Sun belongs to, from much smaller fragments of gas. Instead of birthing giants hundreds of times the mass of the Sun, the universe began producing stars with masses similar to, or even less than, our Sun, which could sustain themselves for billions of years, offering stable environments for cosmic evolution. Furthermore, these heavy elements were the essential ingredients from which the first solid particles of cosmic dust eventually coalesced, and this dust was indispensable for the formation of planets. Without these heavier elements, rocky worlds like Earth, Mars, or Venus could never have been created. And without carbon, oxygen, nitrogen, phosphorus, and sulfur, all born in stars and scattered by their demise, life as you know it would have been utterly impossible. In a grand paradox, the first stars, themselves sterile giants of pure hydrogen and helium, set the stage for the appearance of planets and the eventual rise of life throughout the cosmos. Their brief but violent lives initiated the continuous cycle of stellar evolution and chemical enrichment that persists to this day. But the question remains, how can we, nearly 13.5 billion years later, uncover the secrets of these long-vanished pioneers? Since they all perished long ago, directly observing a population 3 star is out of the question. To tackle this puzzle, scientists adopt several strategies, much like detectives piecing together clues from a very old crime scene. One of the most powerful techniques involves studying living fossils. These are extremely ancient stars located within our own Milky Way galaxy, particularly in its halo, a vast, diffuse sphere of stars that envelops the galactic disk. It is thought that the halo contains some of the very first stars that formed in our galaxy, or in smaller galaxies that were later consumed by it. These ancient stars are classified as population 2. While they do contain small amounts of heavy elements, the quantities are far less than what you would find in the Sun, sometimes thousands or even hundreds of thousands of times lower. The specific chemical makeup of these stars serves as a fingerprint, revealing the composition of the primordial environment from which they were born. By analyzing their light spectra, astronomers can precisely measure the abundance of different chemical elements in their atmospheres. The most fascinating discovery is that the most metal-deficient of these stars display very peculiar elemental ratios, ones that do not match the chemical yields from typical modern supernovae. Some of these unique chemical signatures, such as an overabundance of certain elements alongside a scarcity of others, correspond remarkably well with theoretical models of what the explosions of the very first stars, particularly pair instability supernovae, should have ejected into space. By examining these ancient relics, we are essentially reading the inheritance bequeathed to the cosmos by the population 3 stars. An alternative method is to try and peer directly into the distant past. Since light requires time to travel to us, when you observe incredibly remote objects, you are seeing them as they existed billions of years ago. This principle of look-back time allows us to witness the early universe directly, offering a glimpse of the era when the first stars shone. The deeper you gaze into space, the further back in time you are actually looking, bringing you closer to the dawn of the very first stars. Accomplishing this is a task of immense difficulty. The light from those initial stars and galaxies, no matter how brilliant they were, has journeyed across a vast expanse, becoming exceptionally faint. Crucially, its wavelength has also been stretched dramatically by the expansion of the universe, a phenomenon known as cosmological redshift, which transforms the original ultraviolet and visible light into the infrared radiation that reaches us today. The James Webb Space Telescope, or JWST, was engineered precisely for these kinds of observations. Its massive mirror and unparalleled sensitivity in the infrared spectrum empower it to see farther and detect more tenuous objects than any instrument before it. With the James Webb Space Telescope, astronomers are hoping to finally glimpse the light from the earliest forming galaxies, and maybe even perceive the collective glow from clusters of primordial stars, or the remnants of explosions from that nascent era. The challenge is comparable to spotting the flicker of a candle on the moon. Yet our advancing technology continually moves us closer to achieving this incredible goal. To bridge the observational gap, computer simulations have become an indispensable tool. Since you cannot simply create a primordial star in a laboratory setting, researchers leverage the world's most powerful supercomputers. These machines model the complex conditions of the early cosmos, factoring in everything from hydrodynamics and nuclear fusion to radiation transfer and the properties of dark matter, all based on the initial state of the universe after the Big Bang. In these virtual environments, scientists can watch as the first halos of dark matter take shape, see how gas is drawn into them, and observe the processes of cooling, protostar formation, stellar evolution, and eventual supernova. By cross-referencing the outcomes of these simulations with indirect observational evidence, such as the chemical makeup of ancient stars, the characteristics of distant galaxies, and data on cosmic reionization, scientists can rigorously test and refine their theories about the universe's first suns. This pursuit of the legacy left by primordial stars represents a captivating expedition to the frontiers of knowledge. It weaves together the analysis of our galaxy's oldest relics, the quest to peer to the very edge of the observable universe, and the most intricate of computational models. Although the first stars burned out long ago, their influence persists through their light and the elements they forged, which are now integral to the cosmic structure. Subsequent generations of stars, planets, and even ourselves. They form the unseen scaffolding upon which the grandeur of the modern universe is constructed, and solving their mysteries is fundamental to understanding our own origins. Discovering intelligent extraterrestrial life would confront humanity with a series of profound ethical challenges, forcing a reevaluation of our values, our duties, and our place in the cosmos. The most immediate question would be how you engage with such beings. Would we approach them as equals, or would we attempt to impose our own ideologies and ways of life upon them? This critical issue puts our concepts of respect and coexistence to the test, compelling you to weigh the consequences of forcing our worldview onto a society that could be fundamentally different from our own. There is also the significant hurdle of communication. How can you effectively convey our intentions to an alien intelligence without the risk of misinterpretation that could lead to conflict instead of collaboration? This particular challenge highlights the absolute necessity of carefully constructing any message you send, ensuring it is free of aggression or any sense of superiority. The capacity to successfully navigate this communication barrier could be the deciding factor in fostering peaceful relations built on a foundation of mutual respect. Another critical ethical consideration is the potential danger inherent in making contact. If you do find intelligent life, what obligation do you have to protect not only our world but theirs as well? Our own history is replete with examples where encounters between different cultures resulted in exploitation and immense harm. This forces you to ask whether humanity has the moral fortitude to handle such a momentous discovery with the necessary caution and responsibility. Every single action taken in this new territory could carry monumental consequences for both our species and any alien life we might meet. Finally, you must confront how such a discovery would alter our own self-perception and worldview. An encounter with intelligent extraterrestrials could fundamentally disrupt established religious beliefs, philosophical tenets, and the very definition of what it means to be human, sparking a deep re-examination of life, intelligence, and existence itself. This conversation about the ethical dimensions of contact is far more than mere speculation. It serves as a profound inquiry into our collective character and moral compass as a species. Science fiction has always held a key role in molding public interest and perception regarding the search for exoplanets, which are planets existing outside our own solar system. Narratives of faraway worlds, alien cultures, and interstellar voyages have consistently sparked our collective imagination, encouraging you to contemplate what lies beyond our terrestrial home. These stories in films, books, and television series do more than just entertain. They also inform audiences about the possibilities of life elsewhere in the universe. Popular franchises like Star Trek or films such as The Martian skillfully present sophisticated concepts about space, planetary dynamics, and the requirements for life in a way that is both accessible and captivating. These narratives frequently delve into themes of exploration and discovery, which often mirror the real scientific progress being made in our time. Consequently, as researchers began to actually find and document exoplanets, public fascination soared. The sense of adventure portrayed in science fiction transformed the search for Earth-like planets from a distant scientific possibility into an exciting new frontier for all of humanity. From the concept of the Goldilocks zone, where conditions might be perfect for life, to fictional realms inhabited by intelligent species, these narratives have a way of making abstract scientific principles feel real and understandable. Science fiction has also been a powerful catalyst for actual scientific ventures and missions. Works like Carl Sagan's novel Contact, or movies such as Interstellar, capture the imagination, motivating a younger generation to pursue studies in astronomy and astrophysics. Popular television series like The Expanse delve into the complexities of spaceflight and what living on other worlds might truly entail, igniting conversations in homes across the globe about the nature of exoplanets. Every significant breakthrough in astrophysics seems to trigger a fresh surge of creative narrative, which in turn deepens public fascination. Today, we are on the cusp of potentially identifying habitable worlds, and maybe even detecting signals from intelligent civilizations, making the dynamic relationship between science fiction and scientific reality more relevant than ever. These imaginative tales do more than just mirror our ambitions. They actively shape the public discourse about our role in the universe. Ultimately, the collective sense of wonder about these faraway worlds, fostered by science fiction, enriches both our creative spirit and our scientific pursuits. For a long time, the genre has enthralled audiences with portrayals of exoplanets, which are worlds orbiting stars other than our own sun. One of the most enduring scenarios in these stories involves humanity building settlements on distant planets. In such tales, people are often depicted escaping an Earth ravaged by ecological ruin, conflict, or overpopulation. These narratives present planets with conditions similar to our own, complete with dazzling cities and boundless opportunities for exploration and a fresh start. Another captivating theme centers on the existence of intelligent alien life. Numerous stories explore the idea of a first contact with extraterrestrial societies on exoplanets, forcing us to reconsider our definition of life itself. These plots frequently examine the intricate problems of communication and collaboration as humanity confronts the moral weight of interacting with beings from another world, inspiring you to contemplate what life beyond Earth might genuinely be like. Beyond tales of colonization and alien encounters, fiction often explores the brutal challenges of survival on exoplanets. Authors invent worlds with severe climates and strange biological systems, where staying alive is a constant struggle for human settlers. These kinds of stories frequently serve to emphasize the remarkable resilience and adaptability inherent in the human spirit, pushing our ingenuity to its limits in alien landscapes. Finally, themes of time travel and alternate dimensions are frequently connected to exoplanets. In some narratives, these distant worlds act as portals to different eras or realities, paving the way for exciting adventures that defy conventional storytelling. The heroes in these plots journey not only through the immense distances of space, but also through the very structure of time, allowing for a thrilling exploration of fate, free will, and the consequences of our choices. Artistic renderings of exoplanets often act as a mirror for our shared aspirations and anxieties. Whenever scientists announce the discovery of new planets outside our solar system, the creative community responds with imaginative visions of what these worlds could look like. These artistic creations are far more than simple fantasies. They capture our deepest hopes for the cosmos, stirring dreams of exploration and the potential for discovering life elsewhere. For many, these artworks represent a profound sense of hope, hinting that we might one day connect with other intelligent species or find new forms of life that could inspire greater unity and understanding. Conversely, portrayals of exoplanets can also tap into our fears about the future, illustrating desolate worlds or environments that, while potentially life-bearing, are filled with peril. These images often echo our own planetary concerns, such as climate change and resource scarcity, reminding us of life's fragility. Furthermore, artistic interpretations frequently delve into the philosophical questions raised by the discovery of exoplanets. They pose fundamental inquiries about humanity's position in the cosmos. Are we truly alone? How might contact with an alien civilization alter our identity and moral compass? These questions transcend astronomy, touching upon ethics, existentialism, and our very concept of consciousness, making art a vital medium for exploring what it means to be human. In the ever-growing catalog of known exoplanets, Kepler 186f is notable for a number of fascinating reasons. Uncovered in 2014 by NASA's Kepler Space Telescope, this planet is set apart by its striking resemblance to our own world, which has led many to call it the most Earth-like planet yet found. Among its most compelling attributes is its position within its star's habitable zone, the specific orbital region where conditions are suitable for liquid water to potentially exist on its surface. This particular exoplanet circles a red dwarf, a type of star that is smaller and cooler than our own, and as a result, it gets only about 1/3 of the energy that Earth receives from the Sun. This specific energy level implies that its climate could potentially sustain liquid water, assuming the planet has an appropriate atmosphere. Because of this, it has been added to the select list of worlds that might support life. Furthermore, Kepler 186f measures approximately 1.5 times the size of our own planet, which leads to its classification as a super-Earth. Its larger dimensions suggest it could possess a rocky terrain, and researchers speculate this feature might allow it to maintain a climate comparable to our own, especially if it has a stable atmosphere. These kinds of possibilities spark your imagination and make you wonder about the types of life that could exist in such a place. The finding of Kepler 186f raises profound questions about humanity's position in the cosmos. Through the exploration of these far-off worlds, you can gain a deeper appreciation for the variety of planetary systems and the chances for life existing beyond Earth. Every new discovery pushes you to reflect on how special our planet truly is in the immense universe, and to consider whether distant planetary cousins are out there waiting to be found. Situated about 800 light-years from our world, the exoplanet WASP-121b has drawn considerable interest for its incredibly hostile environmental conditions. This world is categorized as a hot Jupiter, indicating it's a gas giant around the size of Jupiter, but orbiting its star at a remarkably close range. Consequently, WASP-121b endures unbelievably high temperatures, with its daytime side exceeding 2,000 degrees Celsius, hot enough to turn metals into vapor and forge a uniquely extreme atmosphere. One of the most fascinating characteristics of WASP-121b is its bizarre weather patterns. While you might think of weather as rain or snow, on this planet, the precipitation consists of liquid metals like iron and magnesium. This scorching weather is fueled by immense atmospheric pressure, which operates much like a pressure cooker to generate intense climatic events. Fierce winds sweep across the planet's surface at astonishing velocities, creating dynamic and turbulent phenomena that scientists are very keen to investigate. Moreover, WASP-121b displays a dramatic temperature difference between its day and night sides. The side that permanently faces its star is intensely heated by unending sunlight, whereas the other side is cast in perpetual darkness. This sharp contrast gives rise to extraordinary atmospheric dynamics. Scientists propose that heat is carried from the day side to the night side, generating some of the most rapid winds ever recorded in a planetary atmosphere, which can reach speeds of up to 2,500 kilometers per hour. By employing sophisticated telescopes, researchers analyze the changes in light as the planet transits its star. This has allowed astronomers to identify the presence of several elements, such as water vapor, and perhaps even heavy metals. These findings not only deepen our comprehension of this alien world, but also broaden our knowledge about the diversity of planetary atmospheres across the universe. Every piece of data from WASP-121b helps paint a clearer picture of extreme cosmic phenomena, inviting you to contemplate the mysteries concealed among the stars. The discovery of the exoplanet LHS-1140b has fundamentally changed our perception of worlds with the potential for life. This fascinating planet, found about 43 light-years away in the Cetus constellation, is labeled a super-Earth, a rocky world bigger than Earth, yet smaller than Neptune. What makes LHS-1140b so compelling is its position inside its star's habitable zone, where conditions might be just right for liquid water, a crucial ingredient for life as you know it. Unlike many planets of its kind, LHS-1140b is known to have a significant atmosphere, which scientists suspect could hold elements vital for biological activity. Its high density points to a probable solid surface, and studies suggest it might be veiled by a thick cloud layer capable of stabilizing its temperature. This mix of size and atmosphere directly challenges conventional ideas about habitability, hinting that the cosmos might be filled with a wide array of environments where life could potentially arise. The star that LHS-1140b orbits is also a red dwarf, which is known to be more stable than many other stellar types. Although these stars can release radiation that could be damaging to nearby planets, their prolonged, cooler lifespans provide worlds like LHS-1140b a much longer time frame to develop stable conditions and possibly foster life. This realization is compelling scientists to reconsider their definitions of habitability, as worlds outside our solar system may present new variables in the search for extraterrestrial life. Ultimately, LHS-1140b stands as a testament to the immense possibilities that exist within our galaxy. It motivates researchers to widen their search parameters and look at a broader spectrum of planetary settings that could host living organisms. As you continue to observe LHS-1140b and other similar exoplanets, you expand your horizons and intensify your curiosity about what lies beyond Earth. In the field of exoplanet studies, international collaborations have proven to be essential, presenting singular advantages that no individual nation could achieve by itself. These cooperative efforts unite the most brilliant astronomical minds from across the globe, facilitating the sharing of concepts, resources, and technological innovations. By combining their expertise and financial backing, researchers can undertake far more ambitious projects, thereby advancing the frontiers of your knowledge about planets outside our solar system. One of the key benefits of global teamwork is the shared access to a wide range of telescopes and observational instruments. For instance, a facility in one country might house a powerful ground-based observatory, while another nation manages a space telescope that captures different light wavelengths. Making these varied resources available to all partners greatly improves the quality of data collection, giving scientists the ability to examine exoplanets from numerous and complementary angles. I'm sure you're aware that the hunt for exoplanets, worlds circling stars far beyond our own sun, is a vibrant field of modern science. Right now, a number of thrilling international initiatives are in progress, with a leading example being NASA's Transiting Exoplanet Survey Satellite, or TESS, which launched in 2018. Its mission is to scan the closest stars by detecting the slight dimming of starlight as a planet crosses in front. By concentrating on these bright stars, TESS pinpoints potential worlds for more detailed investigation by future observatories. Another major effort is the upcoming Plato mission from the European Space Agency. This project will advance the techniques pioneered by TESS to search for planets like our own orbiting stars similar to the Sun. Thanks to its remarkable ability to monitor thousands of stars at once, Plato will analyze their light curves, providing you with critical information about the size, orbit, and potential habitability of newly discovered planets. Back on our own planet, ground-based observatories are also achieving remarkable progress in finding these distant worlds. Using highly precise methods, they can capture direct images and collect information on their atmospheric makeup. For instance, you have the Keck Observatory in Hawaii, which utilizes adaptive optics to correct for the blurring effect of our atmosphere. This allows scientists to isolate a planet's light and deduce its properties, which helps us understand what these worlds are really like. With technology continually improving, the prospects for exoplanet missions are incredibly bright, especially with instruments like the James Webb Space Telescope, or JWST. This observatory allows for unprecedented analysis of alien atmospheres, letting us search for chemical signatures that could point to water, organic compounds, or perhaps even signs of life. All of these efforts reflect our deep-seated curiosity about the cosmos and our desire to find our place within it. As you can imagine, finding and understanding exoplanets is an incredibly complex task that requires collaboration across many scientific fields. Astronomers are on the front lines, using telescopes to spot these worlds through methods like transit photometry and radial velocity measurements. These techniques have completely changed the game, showing us that worlds with life-friendly conditions might be quite common. But the work doesn't stop there. Planetary science provides crucial context by helping us grasp how these alien worlds form and change over time, using our own solar system as a blueprint. To get an even fuller picture, climatology experts contribute by modeling the potential weather on exoplanets with different atmospheric makeups, which is vital when you're looking for worlds where liquid water could exist. Then, astrobiology brings everything together to tackle the ultimate question: could life exist on these planets? By examining how life survives in the most extreme places on Earth, astrobiologists can develop educated hypotheses about where we might find it on other worlds, pushing the boundaries of what we consider possible. What I find truly fascinating is how the discovery of these worlds has completely upended our theories about how planets come to be. For a long time, scientists built their models based solely on what you see in our solar system, so we expected to find similar arrangements elsewhere. Instead, the discovery of exoplanets revealed an astonishing variety of sizes, compositions, and orbits, forcing us to rethink the entire process. A prime example was the finding of hot Jupiters, massive gas giants orbiting their stars at incredibly close distances, which was a major shock to the scientific community. This kind of teamwork, where experts from chemistry, geology, and atmospheric science come together, is absolutely essential. By combining their knowledge, these interdisciplinary groups can more accurately analyze atmospheres, decode spectral information, and build better models of planet formation, giving us a much more solid understanding of these distant systems. This integrated method is what allows us to fine-tune our ideas about how exoplanets develop and whether they could harbor life. Ultimately, these large-scale international projects do more than just gather data. They cultivate a worldwide scientific community dedicated to this shared goal. They promote the exchange of ideas, spark new innovations, and motivate the next wave of astronomers. By involving young researchers, we ensure that the enthusiasm for exoplanet discovery continues, leading to breakthroughs that broaden our cosmic perspective. Through this global cooperation, you and I get to witness an accelerated pace of discovery, deepening our collective knowledge of these captivating worlds that remind us just how vast the universe truly is. The existence of these worlds upends traditional theories of planetary formation, which long held that gas giants could only emerge in the frigid outer reaches of a star system. These surprising discoveries compel scientists to overhaul their models, seeking explanations for how such enormous planets could arise in such harsh environments, and prompting us to rethink the dynamics at play in star systems across the cosmos. Moreover, the very materials composing these distant worlds have quantum dimensions that we are just beginning to explore. The observation of exoplanets has opened a new frontier for understanding how quantum mechanics, the physics of the very small, influences the climate and atmosphere of a planet. For instance, when starlight passes through an exoplanet's atmosphere, its interaction with molecules produces a distinct spectral signature, allowing us to decipher the atmospheric composition and gain new insights into the quantum behavior of matter under exotic pressures and temperatures. You see, these exoplanets are far more than mere points of light in the night sky. They represent vital clues in a grand cosmic puzzle. They compel the scientific community to constantly reevaluate and improve our current models, showing that our grasp of both quantum mechanics and planetary science is a dynamic field that expands with every new world we find. It's entirely possible that future observations will yield even more profound revelations, completely reshaping our conception of the universe. Imagine the moment we discover life on an exoplanet. It would trigger a complete paradigm shift in how we perceive consciousness and intelligence. At present, we often consider rational thought to be an outcome intrinsically linked to the specific evolutionary journey of life here on Earth. Finding life elsewhere would compel you to ask whether consciousness is just an improbable evolutionary accident or a frequent development across the cosmos, capable of emerging under a wide array of circumstances. Such a discovery might also dismantle the idea that consciousness is solely the domain of complex beings. Picture a world teeming with simple microbes that display a responsiveness suggesting a rudimentary form of awareness, prompting profound questions about the nature of life itself. It could mean that even the most basic life forms possess a primitive intelligence, forcing us to redefine consciousness not as a simple yes or no attribute, but as a vast spectrum of awareness. Encountering intelligent life would incite even deeper philosophical contemplation, as an alien civilization with its own standards of consciousness would present a model entirely different from our own. This could shift our perspective, revealing consciousness not as a pinnacle of evolution, but as a versatile set of adaptations for navigating unique environmental pressures. The search for extraterrestrial consciousness, therefore, transcends mere scientific inquiry, inviting you to reflect on our cosmic role, and perhaps leading to a greater appreciation for the interconnectedness of all life. As far as we understand, the fundamental laws of physics are constant across the entire universe, governing everything that happens on exoplanets just as they do here. These universal principles, from gravity to electromagnetism, dictate the formation, evolution, and behavior of these alien worlds. For instance, a star's gravitational influence determines the paths of its orbiting planets, while its radiation shapes their atmospheric conditions and overall habitability. Consequently, when we discover a new exoplanet, we apply these same established physical laws to analyze its properties. Principles like the boiling point of water, gravitational interactions, and the rules of thermodynamics are our essential tools for interpretation. A world orbiting too near its star will likely be scorched, preventing liquid water from existing, whereas one too distant would be a frozen wasteland, equally hostile to the kind of life you and I recognize. Despite this universal framework, the conditions on exoplanets create an astonishing variety of environments. You can find planets within the habitable zone, where temperatures are just right for liquid water, a crucial component for life. Others might possess dense atmospheres that generate a powerful greenhouse effect, trapping warmth and enabling complex chemical processes. These physical laws are what allow us to decipher the nature of these worlds, whether we are analyzing the atmosphere of a gas giant or the surface of a potentially Earth-like rock, with each new finding bringing us closer to grasping the universe's immense diversity. Discovering systems with multiple planets orbiting a single star offers particularly fascinating insights into the cosmos. These multiplanetary arrangements allow us to observe the complex gravitational interplay between worlds, which provides valuable information about their formation and long-term evolution. Studying these dynamics gives you crucial clues about the very processes that likely shaped our own solar system, and indicates that planets in such groups have a distinctly different origin story compared to those that travel alone. Planets can mutually affect one another's orbits, resulting in configurations that become either more stable or more precarious over immense timescales. These complex gravitational relationships offer scientists a window into the probability of various planetary system types emerging, and help identify potential habitable zones where life could theoretically flourish. In contrast, planetary systems with only a single world shift our perspective entirely, prompting us to question why a star has no celestial companions, or if planets might emerge there in the distant future. These lone planets could also signify distinct evolutionary trajectories, adding to the rich variety of worlds found throughout our galaxy. The discovery of more solitary planetary systems compels us to reevaluate the countless ecological variables that determine a planet's existence, thereby deepening our knowledge of planetary ecosystems. By examining both multi-planet and single-planet systems, you can better appreciate the intricate nature of formation processes and refine our models of how life-supporting planets come to be. As we continue to survey more of these systems, you get closer to solving the universe's great mysteries and identifying the cosmic neighborhoods where life might find a foothold. The gravitational pull between multiple planets can profoundly shape the developmental course of their entire stellar system. As these worlds circle their star, their gravitational fields engage in a complex interplay that alters not just their own orbital paths, but those of their neighbors as well. This constant gravitational negotiation can trigger shifts in orbital shapes, distances, and overall stability over many millions of years. For instance, when a massive planet like Jupiter orbits its star, its immense gravity can sway the paths of smaller adjacent planets. It might secure some orbits while disrupting others, sometimes leading to collisions or even the ejection of smaller worlds from the system. This interactive gravitational field not only determines the destiny of the planets, but also influences the arrangement and movement of smaller objects like asteroids and comets. These gravitational tugs can even affect the host star by altering its rotation and magnetic activity, which in turn can have a major impact on the system's habitable zones and the potential for life to emerge. Exoplanetary systems exhibit a stunning variety of orbits and alignments, which offers deep insights into their formation and internal dynamics. One of the most remarkable observations is the sheer range of orbital shapes. While Earth follows a nearly circular path, many exoplanets trace highly elliptical routes, causing them to swing drastically closer to and farther from their stars. This suggests these worlds often experience powerful gravitational encounters with other planets, which have reshaped their journeys through space. Another fascinating characteristic is the alignment of these orbits in relation to their host stars. Some systems feature exoplanets that circle in a flat plane, nearly parallel to the star's equator, which hints at a relatively placid formation history from a stable, uniform protoplanetary disk. Conversely, astronomers have found systems where planetary orbits are tilted at severe angles, pointing to a more chaotic past filled with close shaves with other celestial bodies or intricate migration patterns. So, what do these varied alignments and orbital shapes reveal about the origins of planetary systems? They strongly suggest that the processes of planet formation are far more tumultuous than we once imagined. A system's final configuration is sculpted by a host of factors, including the star's mass, the presence of other planets, and even the gravitational pull of nearby stars. A densely packed system with numerous large planets, for example, is more likely to produce eccentric orbits, offering crucial clues about the forces at play during its infancy. The incredible diversity of orbits and alignments in exoplanetary systems serves as a window into the fundamental mechanics of astrophysics. By analyzing these features, scientists can decode the story of planetary formation, trace the evolutionary paths of stellar systems, and even assess the potential habitability of these alien worlds. Since the groundbreaking discovery of the first exoplanet in the early 1990s, the field of planetary science has been completely transformed. Back then, astronomers confirmed the existence of a planet circling a distant star, a moment that fundamentally altered our perception of the cosmos and ignited our curiosity about worlds beyond our own solar system. As technology progressed, so did our methods for detecting these distant planets. We initially depended on techniques like the radial velocity method, which identifies a planet by measuring its gravitational tug on its star. Soon, however, scientists developed a range of more innovative strategies. The transit method proved especially effective, allowing us to detect the slight dimming of a star's light as a planet crosses in front of it. Telescopes like Kepler, and more recently, the Transiting Exoplanet Survey Satellite, or TESS, have since expanded our catalog of known exoplanets into the thousands. Our understanding of the kinds of planets that exist has also evolved dramatically. In the early days, our discoveries were dominated by large gas giants, similar to our own Jupiter and Saturn. Today, we observe a breathtaking spectrum of planet types, ranging from scorching hot Jupiters that orbit perilously close to their stars, to rocky, Earth-sized planets situated within the habitable zones where liquid water could exist. This concludes our exploration of how far our understanding has come. The sheer variety of planets forces you to think about their origins, their development over time, and the kinds of atmospheric conditions that could foster life on other worlds. Investigating the atmospheres of these distant planets has become a central focus, especially as you analyze the light filtering through them during a transit. This method allows for the identification of specific gases, which provides clues about a world's climate and its capacity for life. while also offering a deeper look into the mechanics that form entire planetary systems. Your comprehension of the cosmos expands with every new discovery, unveiling a universe far more intricate and varied than you might have previously conceived. If you trace the search for worlds outside our own, you will find its origins are deeply embedded in astronomical history, with the Italian scientist Galileo Galilei standing out as a foundational figure in exoplanet studies. His revolutionary observations in the early 17th century, conducted with one of the first telescopes, fundamentally altered humanity's perception of the cosmos. By studying the planets and moons within our own solar system, Galileo ignited the curiosity of future scientists, leading them to contemplate the existence of planets around distant stars. Later, in the late 20th century, you find the astrophysicist Frank Drake taking a central role in the conversation about exoplanets by creating a method to approximate the number of technologically advanced civilizations in the Milky Way. This formula, which became known as the Drake equation, put a spotlight on the critical need for information about other planetary systems. Its focus on extraterrestrial intelligence generated a groundswell of enthusiasm and catalyzed a new wave of scientific inquiry into these distant worlds. You can also point to the historic achievement of Swiss astronomer Michel Mayor and his collaborator Didier Queloz in 1995. They provided the first definitive proof of an exoplanet, a gas giant known as 51 Pegasi b, circling a star similar to our own Sun. This breakthrough did not just upend the conventional understanding of how planetary systems form. It also unleashed a torrent of new exoplanet findings, completely reshaping the discipline of astronomy. Furthermore, you cannot underestimate the impact of space-based observatories, especially the Hubble Space Telescope and the Kepler Space Telescope, which was launched in 2009. The Kepler mission, in particular, was engineered with the express purpose of finding new exoplanets, and it profoundly enhanced your ability to identify and analyze them. The data from these cosmic inquiries has greatly deepened your comprehension of the universe and humanity's position in it, fueling the drive to investigate other stars and the possibility of life elsewhere. When you look at how modern researchers conduct their work, you see that historical errors about planets have had a major effect on their methods. Many of these flawed ideas stemmed from observations made with primitive instruments, which caused earlier scientists to arrive at what are now known to be incorrect conclusions. For instance, the long-held belief that planets traveled in flawless circles around a central Earth prevailed for centuries, until it was overturned by the work of Copernicus and Galileo. Such mistakes from the past act as a crucial lesson for today's scientific community, emphasizing the need to challenge accepted truths and stay receptive to new information. The shift from an Earth-centered to a Sun-centered model of the solar system represented a pivotal moment in scientific thought. This progression fosters a sense of careful optimism in current studies, compelling researchers to create experiments that meticulously test their theories to prevent similar errors. Acknowledging historical inaccuracies reinforces a healthy skepticism, driving planetary scientists today to confirm their findings with reproducible tests and peer evaluation. These old misunderstandings have also directly fueled advances in technology and research techniques. For example, once you realize that planetary orbits are not perfect circles, it necessitates creating far more advanced simulation models and software. Consequently, contemporary researchers now employ intricate algorithms and cutting-edge instruments like the James Webb Space Telescope to observe the universe with unparalleled accuracy. Recounting the story of how your understanding has changed is vital for training the next wave of scientists. When you integrate the history of these scientific missteps into educational programs, it offers valuable context and teaches a core principle of the scientific method, that knowledge is a process of constant refinement. This approach cultivates an unending quest for information and helps modern research practices resist the lure of easy answers, ultimately broadening the horizons for future planetary exploration. Finding an advanced civilization on an exoplanet would have immense consequences for your future, primarily through the potential for teamwork and sharing information. Imagine you could connect with beings who have developed technologies that far exceed your own. You could learn from their breakthroughs to tackle urgent issues like global warming, lack of resources, and medical emergencies. Moreover, encountering other intelligent life would force you to contemplate the course of your own society's development, perhaps offering lessons on the long-term survival and sustainability of a civilization. The existence of civilizations that have thrived for thousands or millions of years could offer you profound inspiration, suggesting that our own society might endure its technological and social growing pains. Their history could serve as a vital guide, teaching us crucial lessons about resilience, cooperation, and the ethical use of power. At the same time, the prospect of encountering such beings warrants a degree of caution. They might perceive us as an inferior life form, or we could dangerously misread their motives, reminding us that technological prowess is not a guarantee of moral advancement. Considering this dynamic could fundamentally alter our global conversations about technology, surveillance, and humanity's role as custodians of this planet. Ultimately, meditating on the possibility of advanced alien life compels you to engage in deep self-reflection, examining your own values and behaviors. This cosmic perspective could highlight the urgent need for global unity, fostering a shared sense of purpose and encouraging us to become better stewards of Earth, and perhaps more enlightened citizens of a galactic community. Transhumanism is a philosophical movement that champions the use of sophisticated technologies to elevate the human condition, exploring our potential to evolve beyond current physical and cognitive boundaries. This idea gains particular significance when you consider the exploration of distant exoplanets and the search for methods to secure humanity's survival far from our home world. With Earth facing critical challenges like climate change, dwindling resources, and existential threats from space, establishing colonies on other planets is emerging as a credible long-term strategy. In this ambitious undertaking, transhumanists imagine a future in which humans possess dramatically enhanced abilities. These could include superior physical traits, heightened cognitive functions, or even biotechnological adaptations designed to help us flourish in completely alien environments. This forward-thinking vision propels the creation of technologies that would permit humans to withstand the unforgiving conditions of other worlds, such as weaker gravity or extreme temperature fluctuations. Indeed, the study of exoplanets creates a unique intersection where transhumanist philosophy and space exploration can merge. If planetary colonization becomes a necessity, we may be forced to redefine the very meaning of being human. Proponents of transhumanism suggest creating hybrid beings that integrate human biology with artificial intelligence, or using genetic engineering to augment our natural abilities. Such modifications would allow us to adapt and survive in environments that are currently lethal to us. The search for habitable exoplanets is therefore intrinsically connected to the ideals of transhumanism. As you look toward the stars and humanity expands its reach, the concept of augmenting our own capabilities becomes increasingly vital. By fusing technology with our biological makeup, we might not only discover new homes beyond Earth, but also reshape our understanding of what it means to be human in a cosmos teeming with possibilities. As you peer into the vastness of space, the idea of exploring faraway exoplanets fires the imagination. With new technologies rapidly advancing our buoy to understand these remote worlds. One of the most significant innovations is in the field of space telescopes, where instruments like the James Webb Space Telescope are engineered to see deeper into the cosmos than ever before. These powerful observatories can analyze the light that filters through a planet's atmosphere, searching for the chemical signatures of substances like water, methane, and oxygen, which are all potential indicators of life. Another promising frontier in exoplanet studies involves the design of sophisticated robotic space missions, such as interstellar probes intended to travel beyond our solar system to collect data on neighboring stars. These robotic envoys would need to employ revolutionary propulsion systems, like solar sails or ion drives, to traverse immense cosmic distances far more quickly than today's spacecraft. Such missions could provide you with direct measurements of the atmospheres and surface conditions of exoplanets, greatly refining our assessment of their habitability. Artificial intelligence is also assuming a central role in this evolving field. Powerful machine learning algorithms can analyze enormous volumes of astronomical data at speeds no human researcher could match, identifying subtle patterns in light curves that could signal the presence of an exoplanet, or even hints of biological activity. This capability dramatically accelerates the pace of discovery and provides new insights into the potential habitability of worlds we already know exist. Looking further into the future, the concept of a space elevator has appeared as another innovation that could completely transform exploration. This theoretical structure would involve a cable anchored on Earth and stretching far into space, streamlining access to orbit and enabling the launch of larger, more complex instruments for studying exoplanets. Although this technology is still theoretical, its development could revolutionize space travel, making it more efficient and affordable, and bringing the dream of comprehending distant worlds much closer to reality. Imagine how science centers and planetariums can employ immersive technologies, such as virtual and augmented reality, giving you the chance to traverse distant worlds and directly sense the conditions on exoplanets. This approach transforms an abstract idea into something that feels almost real, serving not only to educate but also to spark inspiration for continued exploration and interest in the cosmos. Another highly effective strategy is the strategic use of social media, where scientists and educators can distribute compelling visuals and research updates in easily digestible formats on platforms like Twitter or Instagram. Presenting striking images of exoplanet atmospheres or contrasting them with our own solar system can captivate a wide array of audiences, effectively democratizing knowledge and closing the divide between scientific communities and the public in an engaging way. It is also essential to collaborate with educators to embed the science of exoplanets into school lesson plans, making topics like space exploration and the hunt for extraterrestrial life a core part of the curriculum. By fostering this curiosity at a young age, we can help raise a generation with a deeper appreciation for our cosmic place and the importance of today's astronomical breakthroughs, creating an informed public eager to learn about the universe and our potential stellar neighbors. As our explorations push beyond our solar system, social media has emerged as an indispensable tool for sharing findings with a worldwide audience, which is critical for public engagement. Through platforms like Twitter, Instagram, and Facebook, Researchers can provide immediate updates, breathtaking visuals, and new data concerning exoplanets, igniting the imaginations of countless people. One of the most potent methods for leveraging social media involves the use of powerful imagery and interactive features. Pictures of faraway planets captured by telescopes can be showcased alongside insightful infographics that clarify the discovery's importance. By inviting you to navigate virtual simulations of these worlds, or join in on discussions and Q&A sessions, scientists can foster an interactive dialogue that deeply involves and enlightens their audience. To broaden the impact of exoplanet discoveries even further, partnerships with influencers and science communicators are invaluable. When popular figures in science education share their enthusiasm and analysis of new findings, they connect with audiences that might never read a formal scientific paper. This approach helps to dissolve the barrier between professional scientists and the general populace, cultivating a collective sense of awe for the universe that awaits us. Moreover, organizing special events around major discovery announcements or the anniversaries of key missions can build a shared sense of excitement. Using dedicated hashtags, live streams, and countdowns creates a community experience around these celestial events. By keeping the conversation alive and promoting active participation, social media can turn seemingly remote discoveries into a collective adventure, boosting enthusiasm for astronomy. Educational institutions are absolutely fundamental in cultivating the next wave of astronomers and exoplanet specialists. It is in schools and universities that students acquire the core knowledge and abilities required to investigate the vastness of space. Introducing foundational disciplines like physics, mathematics, and computer science provides the structured learning environment needed to comprehend the intricate dynamics of celestial bodies. Universities, in particular, function as vital centers for research and innovation. Many are equipped with their own observatories and research facilities, enabling students and faculty to engage in direct experimentation and observation. This hands-on experience is indispensable for honing skills in data analysis, telescope management, and research methods, often leading to discoveries that advance our understanding of exoplanets. Mentorship also stands out as a critical function of these academic settings. Professors and established researchers act as guides for students, nurturing their passion for space exploration while offering essential career guidance. This personal support can profoundly influence a student's professional journey, helping them navigate the complex landscape of academic and research careers and opening doors to future collaborations. Finally, these institutions are pivotal in bringing astronomy to the wider public. Through outreach initiatives, public seminars, and hands-on workshops, they invite the community into conversations about space exploration and new scientific frontiers. This not only introduces young minds to the wonders of the cosmos, but also helps build a lasting culture of scientific curiosity, ensuring that the study of exoplanets continues to raise profound questions about the possibility of life beyond Earth for generations to come. For many years, scientists operated under the assumption that any planets we discovered would mirror the basic characteristics of Earth, making them prime candidates for harboring life. As our technology has advanced, however, astronomers have identified thousands of these distant worlds. This ever-expanding catalog of exoplanets reveals a spectacular diversity that forces you to reconsider the vast range of conditions under which life might actually arise. A significant number of these exoplanets are situated in what scientists call habitable zones, the specific orbital regions around a star where temperatures are just right for liquid water to exist, a key ingredient for life as we understand it. Yet, the quest for life should not be confined merely to Earth-like planets within this conventional zone. The existence of extremophiles, which are organisms that thrive in our planet's most severe conditions, strongly implies that life could emerge in settings radically different from our own. This insight encourages scientists to broaden their definition of habitable environments, extending it to places like gas giants or icy moons that might conceal vast subsurface oceans. The techniques we employ to investigate these remote planets also deepen our comprehension of their atmospheres and any potential biosignatures, which are indicators of life. When an exoplanet crosses in front of its parent star, for instance, researchers can analyze its atmospheric composition for elements like oxygen or methane, whose presence could point to biological activity. The study of exoplanets not only emphasizes the potential for life throughout the cosmos, but also prompts you to confront profound questions about your own existence. It reminds us that life might be a common phenomenon, simply waiting for us to find it. This ongoing journey to understand these alien worlds compels us to revisit that timeless question. Are we truly alone in this immense universe? Or are countless other life forms out there, waiting to be found? As you gaze into the cosmos, the search for exoplanets unveils an astonishing variety of worlds far beyond our own solar system. Through a comparative analysis of the chemical processes on these distant planets, scientists are able to extract a wealth of data about their atmospheres, their potential to support life, and even their geological activity. This method helps you understand how the distinct conditions on each exoplanet sculpt its unique chemical environment. Each exoplanet is governed by its own particular set of variables, including temperature, pressure, and chemical makeup. A world orbiting very close to its star will be intensely heated, which results in different atmospheric compounds compared to a colder planet much farther away. Analyzing these variations allows scientists to grasp how different factors shape atmospheric phenomena, from cloud formation and weather patterns to the very probability of life itself. Furthermore, examining volatile elements and molecules, such as water vapor, carbon dioxide, or methane, can provide essential clues about an exoplanet's history. The detection of certain gases might signal ongoing geological events, like volcanic eruptions releasing material from a planet's interior. Conversely, the lack of expected compounds could indicate an environment too harsh for complex chemical processes to occur, thereby refining our models of planetary formation and evolution. It may be surprising, but exoplanets play a remarkably important role in our efforts to understand dark matter and the cosmos at large. By observing these faraway worlds, scientists collect vital information not just about how planets form and whether they could be habitable, but also about how celestial bodies interact with their surroundings, including their gravitational influence, which can offer clues about the universe's invisible mass. When an exoplanet transits its star, causing a slight dip in the star's brightness, astronomers meticulously chart this event. By studying the light curve, a graph showing brightness over time, researchers can deduce the planet's size, orbit, and mass. This information in turn allows for a more precise calculation of the star's mass, which has broader implications for how we map the distribution of dark matter throughout the galaxy. Any anomalies in the movement of exoplanets can serve as telltale signs of dark matter's presence, as clumps of this substance may exert gravitational pulls that subtly alter the orbits of nearby objects. By observing these gravitational tugs, astronomers can infer the location and density of dark matter. In the end, Each exoplanet discovery not only illuminates the nature of these remote worlds, but also helps unravel the mysteries of the elusive substance that shapes our universe, bringing you closer to answering the deepest questions about the fabric of reality. Among the most profound questions you can ask is the one concerning our place in the cosmos. Are we truly alone? Or does a vast cosmic community thrive among the distant stars? The confirmation of life elsewhere would fundamentally reshape your perception of existence and what it means to be human. This discovery would also force you to reconsider the very concept of intelligence, prompting questions about how similar or different other life forms might be from us, and whether they share traits like consciousness, culture, or technology. Such a revelation pushes you to contemplate the sheer diversity of potential life and the universal experiences that might unite all beings across the expanse of space. It brings up critical questions about communication, mutual understanding, and the chances of forming relationships with entirely different kinds of minds. Furthermore, these possibilities have direct implications for your own survival and existence, making you consider if humanity is a cosmic anomaly or just one of countless species flourishing throughout the universe. Contemplating extraterrestrial life may also inspire you to reflect on the remarkable adaptability and resilience of living things, challenging your assumptions about survival in environments that would be considered utterly hostile by Earth's standards. Ultimately, finding life on other worlds could trigger deep philosophical debates about ethics and responsibility. If you were to find intelligent beings, what would be the right way to interact with them? Should you persist in your explorations and attempts to make contact? The knowledge that you share the universe with other thinking beings would place humanity within a much broader ethical context, one that could redefine your attitudes toward each other, other species, and your own planet as caretakers of all life. Philosophical perspectives are essential in shaping how scientists investigate and make sense of discoveries in exoplanet research. At the core of all scientific investigation is a foundational question. What is the true nature of reality? Depending on their philosophical leanings, researchers might interpret the data from telescopes and space probes in varied ways. For instance, a purely materialistic outlook could lead one to focus solely on measurable physical properties, minimizing the more abstract implications. In contrast, a more idealistic viewpoint might encourage scientists to actively search for signs of life or consciousness, shifting research from simply detecting exoplanets to analyzing the conditions necessary for life or developing technology to capture signals from advanced civilizations. Another major philosophical influence involves your understanding of what qualifies as knowledge and evidence. The philosophy of science provides researchers with the tools to interpret their findings, often prioritizing direct observation and repeatable results as the foundation of progress. At the same time, it acknowledges that you need theoretical models, which are themselves shaped by philosophical ideas, to understand sparse or indirect information, such as data gathered through transit methods or spectroscopic analysis. Ultimately, this dynamic interplay between science and philosophy drives a more profound exploration of exoplanets by encouraging you to question your own assumptions. The way you conceive of life, existence, and your own cosmic significance directly affects the questions you ask and the importance you assign to new findings. With every new exoplanet study, you inch closer to a more expansive view of the universe, a journey where scientific rigor is deeply woven into the rich fabric of philosophical inquiry. The discovery of exoplanets, worlds orbiting stars far beyond our own solar system, has profoundly changed how you perceive your place in the universe. Historically, the concept of anthropocentrism, which positions humans as the most important beings, has governed your relationship with the cosmos. Earth was viewed as the unique center of creation, a special haven for life. However, uncovering thousands of exoplanets, many located in habitable zones, has forced you to see Earth as just one of countless worlds that could potentially host diverse ecosystems. This growing awareness compels you to reevaluate your own importance on a universal scale. The incredible variety of environments on these distant planets, some surprisingly Earth-like, others featuring conditions of unimaginable extremity, demolishes the idea that life must conform to the patterns you know. The chance that life could exist in forms you can't even conceive of urges you to confront your preconceived notions and recognize your own limitations. Instead of being at the center of everything, humanity may simply be one of many possible results of cosmic evolution. Moreover, the idea of anthropocentrism is tied to ethical questions about your relationship with Earth and all its inhabitants. The realization that life might flourish in countless forms across the galaxy should inspire you to respect and protect the biodiversity of your own world. It suggests that life emerges independently of human civilization, sparking a vital conversation about your responsibility to safeguard this planet. A wider understanding of life can nurture a deeper appreciation for the intricate web of ecosystems, positioning you as a steward rather than a master. As you continue to find new exoplanets, each discovery serves as a powerful reminder of the cosmos's immense scale and the boundless possibilities it contains. Every distant world challenges you to think beyond your own species and your own world. By adopting a perspective that cherishes all forms of existence, you open yourself up to a far richer relationship with the universe, one that is filled with more mysteries than you can currently grasp. Indeed, throughout all of human history, the idea of life beyond Earth has been interpreted in a multitude of ways across countless different cultures. If you look into the past, you'll see that some ancient societies viewed the stars as dwellings for deities or ancestral spirits, which fundamentally molded their conception of the universe. For many indigenous peoples, celestial objects are central to their creation myths, with the notion of life beyond our world being deeply woven into their spiritual beliefs. This perspective can cultivate a powerful feeling of universal connection, leading you to ponder where humanity truly fits into the grand cosmic scheme. I believe these varied cultural interpretations add incredible depth to our shared understanding of the cosmos, compelling us to investigate the chances of life existing elsewhere. In a notable shift, numerous Western cultures, especially from the Enlightenment onward, started to perceive the cosmos from a scientific standpoint. The concept of extraterrestrial life evolved from mythological tales into a legitimate field of inquiry, grounded in logical reasoning and direct observation. Visionaries like Giordano Bruno and later Carl Sagan urged people to see the universe not as empty, but as a vast arena potentially filled with life. This historical change in perspective did more than just spark scientific curiosity. It also fueled technological progress and exploration, culminating in missions specifically designed to find evidence of life on other worlds. You can see how cultural beliefs directly shape the focus and methods of scientific inquiry even today. For example, a society that holds Earth to be singular and special might concentrate its efforts on finding life on Mars or elsewhere within our own solar system. In contrast, cultures that are more open to the idea of life flourishing throughout the cosmos might champion more extensive searches for life-sustaining exoplanets. I find it fascinating how these different viewpoints can influence everything from research funding and experimental design to the public's enthusiasm for space exploration. Ultimately, as we see representatives from all over the world share their unique interpretations, the scientific conversation becomes immeasurably richer. The dynamic between cultural heritage and scientific investigation fuels our collective drive to grasp not only our own cosmic position, but also the potential for life among the stars. I think this dialogue between tradition and science is what keeps our curiosity alive, inviting every new generation to contemplate what it means to be human in a universe that might not be as desolate as we once assumed. When we collaborate on the study of exoplanets, it opens up an array of thrilling new possibilities and pushes forward our knowledge of worlds beyond our solar system. By combining the resources, expertise, and knowledge of different nations, I've seen how scientists can pursue far more ambitious projects than any one country could manage on its own. This collaborative approach helps spread the financial load, giving researchers access to pioneering technologies that greatly enhance our ability to find and study these distant planets. Moreover, this kind of international teamwork cultivates a rich diversity of thought and perspective, which I see as essential. When you bring different scientific philosophies together, it often sparks innovative new techniques for detecting and analyzing exoplanets. For example, a satellite launched by one nation might be used in tandem with ground-based observatories in another, allowing for far more thorough and complete observations. This cooperation speeds up discovery and elevates the scientific discourse as researchers learn from each other's distinct methods and experiences. Sharing data on discovered exoplanets is another key benefit, as it builds a deeper and more reliable foundation for our understanding of these worlds. When you have scientists from around the globe adding to a common database, it permits more exhaustive analysis and boosts the odds of making truly significant finds. I'm convinced this inclusive strategy is crucial for improving our grasp of planetary habitability and the complex web of factors that determine a world's atmosphere and surface conditions. Finally, international collaboration serves as a powerful catalyst for public excitement and support for science. Joint missions present a picture of global unity that can ignite the imagination of people everywhere, promoting both education and scientific engagement. When you see researchers from many different backgrounds presenting their findings together, it highlights humanity's shared endeavor to explore the cosmos, reinforcing a common purpose that ultimately benefits us all. This voyage into space is not merely about discovery, but about what we can accomplish when we work as one. I want you to appreciate how the study of exoplanets, those distant worlds orbiting stars far from our sun, provides us with an incredible lens through which we can understand the dynamics of planetary systems, including our very own. By scrutinizing the varied atmospheres, geological structures, and potential climates of these alien worlds, scientists can uncover vital clues about the fundamental processes that govern the formation and evolution of all planets. This method of comparative planetology deepens our comprehension of Earth's own distinct qualities and the modern challenges we are confronting. For instance, examining exoplanets that exhibit extreme greenhouse effects offers us a practical lesson in the consequences of climate change here on Earth. Some of these worlds possess incredibly thick atmospheres that trap enormous amounts of heat, resulting in conditions completely hostile to life as you and I know it. Observing these planets gives us a stark warning about the delicate equilibrium of our own atmosphere, highlighting the critical role of greenhouse gas levels and their long-term effects on our climate. This knowledge, in turn, can help guide our efforts to tackle global warming and other environmental crises. Beyond that, observing the geological activity on other planets gives us a much wider framework for understanding Earth's own tectonic forces. You'll find that many exoplanets show signs of volcanic activity or possess unique surface features that act as parallels to Earth's geology. Studying these distant phenomena allows scientists to better piece together the puzzles of plate tectonics, mountain building, and the ways planetary surfaces change over time. These cross-planetary comparisons ultimately make Earth's own processes, including natural disasters like earthquakes and volcanic eruptions, more understandable within a larger cosmic context. You see, the entire quest for life beyond our world fundamentally relies on our grasp of what makes a planet habitable. By investigating which exoplanets reside in what we call the Goldilocks zone, an area where conditions are perfect for liquid water, I believe we gain a much clearer perspective on why Earth is such a precious oasis in the immense expanse of space. These explorations not only deepen our understanding of how planets form and evolve, but they also give us vital clues for protecting our own world's delicate ecosystems from increasing environmental threats. As we venture further into the study of exoplanets, I find there are several thrilling discoveries on the horizon that are set to redefine your understanding of the cosmos. The search for worlds that could potentially harbor life is truly at the vanguard of this research. We're not just creating a list of new planets. We are actively probing their atmospheres and chemical makeup for the precise conditions that might sustain life. Instruments like the James Webb Space Telescope will be absolutely pivotal in this effort, giving us the power to analyze the air of these distant worlds for traces of water vapor, methane, and other essential indicators. Another profound insight emerging from exoplanet studies is the sheer variety of planetary systems out there. It turns out that our own solar system, with its relatively neat structure of rocky and gaseous planets, is just one of countless possible arrangements. Astronomers have uncovered systems with gas giants orbiting incredibly close to their stars, as well as astonishing planets like super-Earths and mini-Neptunes. Every new find expands the catalog of planetary diversity and orbital mechanics in the universe, forcing us to completely reevaluate how planets are born and how they migrate. As our technology continues to advance, you can expect us to examine exoplanet atmospheres with a level of detail that was once unimaginable. The ultimate objective for future missions is to pinpoint chemical biosignatures, subtle clues that these worlds might host or once have hosted life as we understand it. The capacity to spot complex organic molecules and decipher the light spectra from these remote planets could unlock secrets about evolutionary pathways and even the possibility of entirely different forms of life. Ultimately, the exploration of exoplanets forces you and I to confront some of the most profound philosophical questions about our own existence. With each new piece of information about these far-off worlds, we have to consider the immense implications of finding life beyond Earth. The very realization that we might not be alone could fundamentally alter our perception of life itself, compelling us to broaden our definitions of what it means to be habitable or intelligent. Every discovery doesn't just contribute to our scientific knowledge. It strengthens your connection to the cosmos, reminding us all of the wonders awaiting us beyond our home. I think the documentary format is an exceptionally effective medium for enhancing public appreciation of the complexities surrounding exoplanets. By merging breathtaking visuals with engaging storytelling, These films vividly conjure the vast and enigmatic worlds that exist outside our solar system. This form of visual narrative truly captures your imagination, helping you picture what these planets might look like, how we find them, and what specific conditions make each one so unique. When you can visually connect with these distant worlds, it inspires a genuine sense of awe for the universe. Documentaries also excel at breaking down intricate scientific ideas through expert interviews and clear, relatable explanations. By putting you face to face with leading scientists and astronomers, filmmakers can demystify the complex details of astrophysics and planetary science in a captivating way, making technical procedures like the transit method or radial velocity easy to understand. This method doesn't just educate, it also shares the collaborative passion of the research community, bringing the excitement of discovery right into your home. The deliberate pace of a documentary also provides the space to explore deeper themes, inviting you to contemplate the more profound questions about life in the cosmos. By skillfully weaving together the narratives of recent breakthroughs with the historical progression of our planetary knowledge, these films can emphasize our ongoing journey as cosmic explorers. This creates a powerful feeling of connection, prompting you to think not just about what exoplanets are, but what they truly signify. A beckoning from the universe to continue our relentless search for knowledge among the stars.